Welcome to our show, A Level Chemistry Today. May I welcome our celebrity guest, Her Royal Highness, Queen Elizabeth II.
Oh, Albert, it is such a pleasure to be here. One really can't wait to get started discussing today's topic, attacking species in organic chemistry.
As we all know, chemistry is about opposites attracting.
Yes.
Today we will look at three types of nasties: the free radical,
The nucleophile.
and the electrophile.
Let us first look at how free radicals are generated. From the diagram, Albert, you can see that the chlorine bond is absorbing energy. You do know what energy is, don't you, Albert?
Yes, Your Majesty, I know a thing or two about energy. It is likely that the bond has absorbed a photon of just the right wavelength to excite its electrons. This causes the two chlorine atoms to pull apart so that eventually the bond breaks.
You appear to me more intelligent than you look. Homolytic. I bet you can't explain what that means, Einstein.
Okay, Liz. Each chlorine atom gets an equal share of the electron pair in the bond. There is a mistake in that diagram. There are two double-headed arrows. We'll discuss that later. When the bond undergoes lysis or breakage, each atom ends up the same, each with an unpaired electron, hence the prefix homo.
No need to be on PC, Albie.
No, Your Highness. There is another type of bond breakage we call heterolytic fission.
And I suppose that's when two different species are formed.
In a heterolytic fission, both the electrons shared in the bond go to one atom, almost always the more electronegative atom. Here I will draw a simple molecule that has a dipole. The atom which is attached to the carbon is more electronegative. That is, it is drawing electron density within the covalent bond towards itself. When it breaks unequally, two different species are formed. An anion with both electrons from the pair and a cation, positive ion. The more electronegative atom will win the pair. Notice that the curly arrow here has a double head. It is showing the movement of the electron pair within the bond onto the more electronegative atom. Unlike free radicals, with unpaired electrons each, the ions formed do not attack other molecules randomly. Instead, they will be attracted to other species of opposite charge or polarized in some form or other. Have you got heterolytic fission, Lizzie?
Yes, I've gathered that free radicals are highly reactive species with unpaired electrons. I have also gathered that they are formed in homolytic fission. Heterolytic fission produces ions of opposite charge. How reactive are free rads, Albert?
Free radicals attack anything. Think about what chlorine radicals have been doing to the ozone layer before that ban on CFCs. Think about free radicals attacking an aging skin to pair up electrons. People like you and Philip grow old gracefully, but you can slow down aging by preventing free radicals attacking your skin. Avoiding too much sunlight is one way, or using a protective sunscreen is another. Let us now look at the concept of nucleophiles and electrophiles.
We have with us today our Mancunian roaming reporter, Priestley College's chemistry teacher, Wendy Winard. Oh dear, Albie, I hope we can understand that dreadful accent. Over to you. All right, Your Majesty. All right, Mr. Einstein. I'm over here to help explain to our viewers about those other attacking species. I'll try to talk proper, but if you don't understand, just chip in. For a better explanation, let's go over to our friends, the attacking species themselves. You can see here all of the attacking species. Well, first of all, we've already met the radical, and we know that the radical here, this little monster, is a highly reactive species with unpaired electrons. They will attack almost anything in order to pair up their electron. The nucleophiles, however, are a bit more particular. What they will do is they will attack and any electron-deficient carbon atom in the vicinity. So if that poor carbon's attached to a highly electronegative atom, they will attack. The electrophiles are opposite to the nucleophiles. So you could also consider the nucleophile here as part of the electrophile itself. A nucleophile will donate a pair of electrons, and an electrophile will accept a pair of electrons. There it is, ripping off this pair of electrons.
A satellite link to some species in a test tube.
Nucleophile.
I think we got hold of a nucleophile. He claims it can turn into a base. We've got an electrophile.
And finally, the species that you didn't mention was a base.
Hello, how are you?
I'll let you come
I am a nucleophile. I like to attack electron-deficient carbon atoms. When I get there, I kindly donate a pair of electrons to form a bond.
Hello. How do you do? I am an electrophile. I like to attack electron-rich areas and steal pairs of electrons.
Just to remind you, I'm a free radical. I attack anything and I have unpaired electrons.
If I am in high enough concentration, I will also run off with weakly held hydrogen atoms. Protons to you chemists out there. I am then known as a base.
Well, that was very interesting. Do you now know about all of the species, Your Majesty?
Yes, Mr. Einstein, I have learned so much today. I know that a free radical is a species with an unpaired of electrons, with unpaired electrons that will attack anything.
Correct.
I also know that nasty nucleophiles will attack poor defenseless electron-deficient carbon atoms by donating a pair of electrons.
Well done.
And an electrophile donates a pair of electrons?
No, you silly woman. An electrophile attacks electron-rich areas and steals a pair of electrons.
Okay, don't get your knickers in a twist, Albie. An electrophile attacks electron-rich areas and steals a pair of electrons. And in some way, it's the opposite of the nucleophile.
You've got there at last, Your Majesty.
Well, we've come to the end of the show, and it's time to say goodbye. Goodbye.
And it's go-bye from me.
And a jolly farewell from me. Until next time, when we look at how those attacking species attack. See ya, ta-ra!